This module covers Newton's laws, and some of Newton's laws are pretty easy to understand, and some of them initially kind of make us scratch our head. We'll start with Newton's first law, which is a pretty good place to start with the first one. And Newton's first law says that an object in motion or at rest tends to stay in motion or at rest unless acted upon by an outside force. Now, first of all, what's a force? A force is simply a push or a pull on an object. And so we can easily understand the part that says an object at rest tends to stay at rest, because we know that an object that's sitting still doesn't tend to just start moving for no apparent reason. So we can see that a box sitting on the floor is going to stay a box sitting on the floor. It's not just going to start moving unless something else happens first. The part where it says an object in motion tends to stay in motion probably makes us pause, because we know that if we take a box and we give it a good hard shove so that it goes moving across the floor, we know that the box doesn't keep moving forever, it stops. Think about something that's moving in outer space. If you have an object that is going through outer space, say that, when NASA puts some sort of a rocket into space, once it escapes the Earth's atmosphere, gets far enough away from the Earth so that it is no longer being affected by the Earth's gravity, and it's out far enough in space, that rocket no longer has to keep firing its rockets in order to keep moving in a certain direction. Once it's moving in that direction, it keeps moving in that direction forever. There's nothing out there to stop it from moving. On Earth, however, there are lots of things to stop motion, and we don't always recognize initially what those forces may be. The box that I mentioned moving across the floor, friction is actually acting on that box. And we'll talk a lot about friction a little bit later on in this module. But friction is actually a force, and it opposes motion. It stops motion from happening. Air resistance is a type of friction, and so that also is going to stop objects from moving, because it also is a force. Now, Newton's second law gives us a little bit more, a quantitative understanding of how these forces are going to work. Newton's second law says that the vector sum of all of the forces acting on an object is equal to the object's mass times its acceleration. If I get my tongue untangled. So the sum of all the forces, now this is simply the Greek letter sigma, which means in mathematical symbols the sum of, is equal to the mass times the acceleration. Now again, this is one of Newton's laws that's relatively easy to understand. Picture an office chair with wheels on the bottom of it. If your dad is sitting on the office chair versus if your little sister is sitting on the office chair, if you're trying to give your dad a shove and get him to go moving across the floor, you're going to have to shove him a lot harder than you are to get your little sister moving across the floor. Your dad has more mass, so it requires a greater force to get him to move. Now, picture just your little sister, and maybe you're trying to keep her entertained for some reason or other. And so initially when she's sitting on the office chair and you give her a shove, she goes, kind of slowly across the floor, but she giggles and she thinks it's really funny. And so she goes, faster, faster, push me faster. Well, in order to give her a faster acceleration, you know that you're going to have to give her a harder push. So the greater the mass, you have to push with a greater force. If you want the object to have a greater acceleration, you're going to have to push with a greater force. Now, these are vector quantities. So a force is going to be in a certain direction, and acceleration is going to be in a certain direction. We've already talked about how acceleration is always in a certain direction, but that means that the force is going to be in a certain direction too. And the direction of the acceleration is also the same as the direction of the force. Now let's go back to the box, because that's where things start to get a little fuzzy for us sometimes. Remember that acceleration does not necessarily mean that something is speeding up. It could very well be slowing down, because acceleration just means a change in velocity. So if you've got this box and you've given it a push and it's sliding across the floor this way, as it goes this direction, the velocity is going to go down. And we talked about in the first couple of modules how if the velocity is slowing down in this direction, that means that the acceleration must be in this direction. The velocity is positive, but the acceleration is negative, so that means it's acting this way. Well, from the perspective of friction, friction opposes motion. So if motion is this direction, friction acts this direction. So in that case, we already said velocity goes this way, acceleration is going this way, and the friction acts in the opposite direction of the motion. So the friction is acting in that direction also. So yes, it is true that acceleration and the applied force are always going to be in the same direction. Now, what units are we using for force? Well, in general, mass can be expressed in a number of different units, but the SI unit for mass is kilogram, and for acceleration, the SI units are meters per second squared. So if I have a kilogram meter per second squared, that has been defined to be equivalent to 1 Newton, obviously named after Sir Isaac Newton, who came up with these laws. Okay, so this is the general unit force that we're going to be using. However, any mass, any length, and any time unit squared can be used for a unit of force. If I wanted to use a gram and a centimeter and a minute squared, that would also work for a unit of force. It's just that it wouldn't translate into a Newton. Only a kilogram meter per second squared will translate into a Newton. So let's look at example problem 5.1. This is a pretty straightforward example of Newton's second law, of using Newton's second law. A person pushes a rock with an acceleration of 0.12 meters per second squared to the east. Meters per second squared east. And again, here's that direction. And so if the acceleration is in that direction, that means the force is going to have to be in that direction also. It says the rock has a mass of 4.2 times 10 to the 4th grams. And it asks us what force the person is exerting to move it. I'm going to go ahead and work this so that the answer is going to be in newtons. And so that means, first of all, I've got to change my mass from grams to kilograms. You may be to the point now where you can pretty well do this in your head. If you can't, then you know that 1 kilogram is equal to 1,000 grams. And so that's going to give me an answer of 42 kilograms for my mass. So if I want to calculate the force is going to be 42 kilograms times 0.12 meters per second squared to the east. And the force, when I multiply 42 times 0.12, I'm going to get 5.0 newtons, and that will also be to the east, again, because the acceleration and the force are going to be in the same direction. Okay, two significant figures, because both of those had significant figures, so you have to make sure you express it as 5.0. Okay, so those are the first two of Newton's laws. Hopefully those laws are relatively clear. We're going to spend a lot of time working on the mathematics behind Newton's second law as the module progresses.